going to do a problem involving a phase change, so we can use that equation we just learned. We do need to notice that this is asking about vapor condensing, but this is a heat of vaporization. In other words, we know that from the liquid to the gas, the heat of the reaction is 27.2 kilojoules. But if we're looking at the substance condensing, the opposite reaction, then the heat of this reaction is going to be negative 27 point. Just like we learned when you flip the reaction, you flip the sign on the heat of the reaction. Okay, next thing we want to do is figure out our Q, and this is our Q for our reaction. This is not the Q that it's giving to the environment. This is the Q for this substance. And we always assumed that delta H for the reaction is equal to the Q for the reaction. We did that because we assumed there was no PV work. Anyway, so let's calculate our Q for this reaction. And really this is really too simple because it's just 1 mole, but I'm going to go ahead and show that in case you have a problem that isn't 1 mole. It's pretty simple. This, I guess that one, that is per mole. And so, like I said, this is pretty simple. Okay, and again, this is this is the same thing as delta H for the reaction for what we're doing. This is because this is still reaction here. Okay, and then next step is that we can use this equation. And again, we're calculating the change in entropy for the substances, not the surroundings for this. And so this Q here is basically our delta H for the reaction. Same thing. And so we're just going to do, now for the temperature, we were given a temperature of 25. But we need to make sure we put that in Kelvin. And we do need units here. This is kilojoules. And I'm going to rewrite this because I'm going to put it in joules. It's a small number, so change in entropy for the substances and so notice that we now know our units for entropy. It's energy per temperature. Joules per K is the typical. Okay, and then we could ask ourselves, does this make sense? So this means that as far as it being negative, let's think about what that means. If we have entropy and we're going from a gas to a liquid, are we going to expect it to drop in entropy to go from that gas to a liquid? And we do. We would, because so the delta S is negative. Because we know that a gas has more entropy than a liquid. So we would expect that number to be negative. Okay, let's see what else we can do with this. So given we're going to use this, and this is per mole, by the way, because we were doing per mole. So I'm going to go ahead and put the mole down here. And so what we're doing is we know the delta S, this right here, we know this delta S, and we're going to compare these two values, the gas and the liquid values. And here I'm given this number up here, and I know what the change is, so I can calculate the entropy of the liquid. So in other words, I know that the change in entropy for the substance is going to be equal to the entropy of the liquid minus the entropy of the gas. And how I got that is that this is kind of the final, and this is the initial. So we'll plug in our number. And we were given, we don't know this one, but we were given the entropy of the gas. Looks a little bit. There we go. And so we're just going to solve for the entropy of the liquid. So you can see that these entropies are values, number values, just kind of like we had the heat formation. We had a number for each substance and how much enthalpy it had. This is how much entropy they have. Okay, and then we can say, does that make sense? We're starting with our gas and going to our liquid, and our gas's entropy is 243, it's up here, and our liquids, this is the gas, is 152, it's down here. And so that's what we had expected, is that we should have a loss in entropy going from a gas to a liquid.